Sarah Bals, and we are here at EMAT, which is the electron microscopy group of the University of Antwerp. I'm standing in front of a very special transmission electron microscope. It's our quantum microscope, and quantum is the acronym for Quantitative Antwerp Electron Microscopy. The reason why this microscope is so special is that it is one of the most stable electron microscopes around the world. It's an aberration corrected microscope, and it has a spatial resolution of 50 picometer. In addition to that, we can operate the microscope at different acceleration voltages, and low acceleration voltages are of great importance if we want to reduce electron beam damage, which is especially important if we want to investigate soft materials, as is the case in the EUSMI program.
Electrons are negatively charged particles orbiting around the positively charged nuclei of atoms. With the help of such electrons, the quantum microscope can enlarge objects to an extent that the positions of atoms in a material can be read out, so to speak. In order to be able to look at objects with the quantum, a small specimen, a sample, is taken from the material. In the quantum, electrons are accelerated to very high speed and then projected onto the sample. The electrons pass through the material and store images of the atoms they meet along their way. So the electrons can read the atoms and the structure of the material.
We are looking now at a material, and with this transmission electron microscope, if we increase the magnification sufficiently to about 5 million times, we can see the structure of the sample down to the atomic scale. That information allows to learn a lot about the properties of the material and to know how it functions.
What we are doing at the electron microscopy lab in Antwerp is study the structure and the composition of materials, nanomaterials and soft materials. And we do that using transmission electron microscopy. Now, conventionally, this technique only provides a two-dimensional projection of what is in reality a three-dimensional object. And therefore, within EUSMI, we will also apply electron tomography. The idea behind this technique is similar to a medical scanner. So we will take different projection images of an object every time tilting that object. And then we will collect all of the images and use them as an input for a mathematical algorithm. And in this way, we will obtain a three-dimensional visualization of the object. Our task within the program is to expand that also from looking at the structure to the composition of the materials. It's very important to obtain quantitative information. So we want to move from looking at images to extracting numbers. In addition to that, we want to make sure that we investigate the materials under relevant conditions. So the conditions at which they are used during application. And in order to reach that goal, we will collaborate closely with another partner, Then Solutions, who will be building holders to simulate the real environmental conditions of the nanomaterials. If you think that transmission electron microscopy could be of use for the research at your institute or company, then don't hesitate to apply for transnational access, because I really believe that it's beneficial for all parties.